Hello everybody, welcome to the Global SMT and Packaging Show live from Productronica 2025. I'm very glad to be here, and together with my experts here we will be discussing design for test and reliability and how we prove that designs work. Welcome with me the Patrick Jäger. He's trainer and coach and consultant in reliability engineering for more than 20 years in various industries and also in electronics. And he's one of the CEOs of Reliability Engineering Academy here from Germany. To my far left is Ram Wissel. He is Vice President of Global Technology at Kaizen. He is a veteran in industry, more than 25 years, a chemical engineer, and has helped customers to improve their cleaning and cleanability of products, to improve reliability ultimately, and so he is very experienced also in that field. Today we are going to improve and to talk about how reliability starts in design and what we can do about it to ultimately improve product reliability and reliability of applications in the field. Now, to start off, I would like to ask you about the reliability concept that you are passionate about, and just to get to know you a little bit, what you like most, or what you really feel is fascinating in this field and in your specific fields in reliability engineering and cleaning.
Who wants first? Then I go first, okay. Well, I would say reliability is ensured by doing many things right. The bad thing is that everything can go wrong just by forgetting one single thing. And so if you ask, what is the thing I like most, then I would answer, the thing I would like most is that the companies have a thorough plan which considers all the necessary issues, that they follow kind of a process actually that enables them to really getting better and not committing too many problems.
All right, so it's about having a concept and make sure you do the things right, rather than you can probably not assure that things go right, but you can at least do it in the right way.
Exactly.
Right.
That should be the point.
Thank you very much. Ram, what do you think about it?
Reinhardt, thank you for setting up this panel. This is going to be a fun discussion. One of my passions with reliability is that it's an ever-evolving challenge. It's not a 1 + 1 always equals 2. It's today that's true, but your process and the components, the material sets, the regulations around what we do is always changing. And so it's a challenge. It's new every day, every week. And so as an engineer, it's a lot of fun of educating, working with people, and just always trying to advance the edge.
Great. Well, let us dig deeper a little bit here, because you have obviously seen a lot of things all over these 25 years. Can you take us into this journey and explain a little bit how the applications and how requirements towards cleanability, reliability have changed? Like, what changed that today this is probably more relevant than ever?
I'll start with that. Thank you. The J Standard 001 put out by the IPC, as you're qualifying a new manufacturing process, or if your process has significant changes, you need to create some objective evidence. There's not a hard, this is the way you do it. You have to create what's good for your product, in considering that end use environment. And the key for reliability is understanding what that device is going to experience in the field, and how you can optimize its manufacturing process to be economical and reduce the total cost of ownership, but also for that end use environment. So it's optimized.
All right, so I feel there is, as far as I understand you, there is no one size fits it all solution. it depends on application.
Correct, and that's why they called the IPC called this the objective evidence. So what I'm building, I need to create a set of data that is related to what I'm making. Now, you might be making something a little bit different, and so based off of your device, you might have a different pass-fail criteria. And so it's not a one-size-fits-all. It's really unique to that application and to that. So it's that constant evolving challenge. And specifically, we're talking about ion chromatography testing or SIR testing that measures the amount of contamination potentially that's there, but also provides some evidence of the electrochemical potential that might occur if it was in a high humidity environment.
So I understand the WO standard, WO1 standard is basically more some kind of a methodology rather than a set of rules that you need to stick to.
Correct. It says you need to do certain. You can decide what testing you need, but you have to create a set of data that says that your product is going to be reliable based off its end use needs.
Right, but that means that you need to be aware of now what the application's requires actually.
Yeah.
And yeah, so no one size fits it all solution, but a set of methodologies maybe to approximate towards that goal.
Correct.
And how has electronics changed or evolved throughout the last 20-25 years, and what has changed also towards your direction? How does methodology or your methodologies help? And what can we maybe learn from other industries where you're also involved in, so we can learn from other industries in electronics?
Well, what I can say about that is when we train our reliability engineers, so Reliability Engineering Academy is about training reliability engineers which are able to assist and support the overall design, project management, validation process. So it's an integrated task. And it's like what Ram said, if you have changes, you might buy into new problems. You must be specific about your product, right? When you change something, you might buy a new damage mechanism, which you were not aware before. And the core point, or one of the central ingredients, what we say is important for a good reliability process, is that we deal with the damage mechanisms and that we really deal with the changes in the design, not only in the design, also what Ram said, it's also about understanding what happens with the product in the field. It's about the operational profile. Do I sell the product to a customer now which has dewing, for example? Things like that. So there are some basic principles, and I would say it's a good idea to really think about the deltas between the old and the new design and what damage mechanisms might be there additionally, and really to care about these changes. I would say that's quite a good recipe.
All right, so when we talk about design for test or reliability, the idea sometimes could come up, we do some simulation and then we are done. Like what you just suggested is that you work, you make use of the delta object, like you document it and then learn from it. Also repeatable learning curve, and then apply it possibly to another project.
Exactly. Yeah, it's about permanent learning actually, but really the chance to have the chance and the time in the development process that you really can deal with the changes.
Right.
And that also has as a prerequisite that I do not permanently change everything, right? So that's quite funny because we have somebody here sitting in front of us with Ram from the company Kaizen, which in Japanese actually means systematically, slowly getting better and better, right? And that is the Japanese idea and philosophy of product development. They do not permanently change everything. They change slightly, stepwise, and have enough time to really care about the deltas, right? And that's a good idea. And of course, if we are in a framework where we have to change everything, it's challenging. But still it's the same thing. Each and everything starts with the damage mechanism, the one bad thing.
So I have 2 comments on that. How can we, if we, let's say, improve only like incrementally, how can we improve, or is it possible to achieve a global optimum, or do we end up in the local optimum of reliability, or let's say system reliability, where you usually have multiple optimization criteria, which is cost, which is quality, which is reliability, which might also be other usability. I don't know, like other criteria. Like, how can we deal with that? Or, yeah.
Thank you. I will try to jump in here. It's hard to optimize for one thing without having consequences on the others, and so
Right.
I like your term of optimizing, many smaller optimizations, and that's really the purpose of a lot of DOEs, they're designed for experiments, where you're trying to understand those critical variables in that.
Right.
I like to think of this discussion, there's the design piece up front, and then there's the manufacturing. And so it's really about a process. And I use the analogy of a 3-legged stool, where you might have a really great cleaning process, specific to the cleaning, where it's a great machine and a great chemistry, but you might have a design that's just simply too dense or too complicated to clean effectively. And so at the very beginning of this process, the design piece is wonderful, and I like your education, where you're able to start to design with some guidelines or some rules for manufacturability and improving cleanability for the best reliability.
Right. You mentioned earlier that you need to be aware of the mechanisms, of the failure mechanisms, when you choose test sets, when you choose reliability tests like SRR, SIR, and so on. There is environmental parameters and conditions. What is the number 1 failure mechanism you wish the people would be more aware of? Or maybe not the number 1, but like 1, 2, 3. Like, could you give us an idea of what the design engineers should be aware of and has most impact on their design reliability?
Yeah. Okay. You might guess the answer already. It's like Ram said, we have so many variables in that game that I am not able to give an answer to that in terms of saying conductive phenolic filament would be a critical one, or solder joint breakage, or whatever. They're permanently there. Each of that bad child is always there. And the only chance we have is to get aware which might become more critical in this and that project for us, right? So, yeah, it's an ongoing task. You really cannot say this and that is the critical one. What I would say also is that in terms of reliability assurance, you have basically always 2 ways. The one is you can compute or simulate whatever you can. And the other thing we do not know is what Ram said, it's testing, right? But in terms of testing, that's also interesting. I would say each testing should be there for a purpose. And what I see out in industry sometimes is that testing is just done for its own purpose. It's done because it can be done, right? And that's an interface between development and testing, right? To give the test department a task because of what we found in engineering. And I would say that's beneficial.
Following up on that, and I think a lot of it is communication and understanding. I think if you've ever worked on your car, you might have experienced why is that spark plug way back here where it's really hard to reach? Well, the guy in the design at his CAD level said that's no problem, but there's a manufacturing piece that becomes very difficult. I think here a little bit more collaboration between the component design engineers, the PCB design engineers, the manufacturing engineers, where there's a lot of assumptions. Oh, that will get fixed, or that will be okay. This is what my data sheet says, and as long as my data sheet says that, then it's okay. But it's that wisdom, it's that application, some collaboration. I think having some teams to solve these challenges and share that appreciation will help on both sides.
Yeah, I think one of the big things is to probably educate designers that the world is not as shiny and as nice and perfect as in their ECAD system. So you have tolerances, you have environmental impact, and is there any methodology how you would approach if you have a new product and you need to set up some testing, some reasonable testing, as you just stated, to ultimately make sure that the application is suitable for the requirements throughout the lifetime?
Well, basically, we have to distinguish between a new product and a product change, right? And the main portion actually of development tasks are product changes. So it happens quite seldomly that you really have a grassroots project where you develop everything new. In such a case, the message will still be the same. We need to understand damage mechanisms. Of course, we will benefit from a large variety of validation tests, and we do them. That's okay. But too many people lean back on the idea that, well, our testing processes are sufficient. That means when we pass all the tests, we are done. We are safe. We have too many customers that approach us and say, well, we passed all the tests, but yet have problems in the field. So that's in case of the new product. And if I have changes, I have a reduced amount of changes, which then I can invest much work in, do a more specific discussion. And what Ram said is very important. It's about the collaboration, right? So who is doing that? My experience is that typically in industry, the classical design engineer, they have just not enough time to do all that, to really serve all that interfaces. And that is the position where I would say reliability engineer becomes important, right?
Well, you asked earlier about some of the failure mechanisms, and I want to go back to the concept of ECM, or electrochemical migration. In the field, you know, what's required there? Well, it requires three things. You have to have a current and energy, and again, we're using our electric devices with the power on. You have to have some level of contamination, ionic contamination, and then you have to have an electrolyte, normally the form of moisture or condensation or humidity. And so that's that chemical humidity electrical bias that's recommended in the J standard. Which of those can you control? Well, again, the power switch needs to be on when we're using our phones. So we can't control the weather. It's snowing outside today. It's beautiful. But if we were outside in kind of a harsh, cold environment, that's it. It's controlling the variables, identifying those factors and what you're teaching to, and understanding what I can influence and what I can't in that targeted end environment.
Right. So basically, we need to figure out, or we need to pre-think which of the environmental stress and from the application, we kind of need to simulate that and press this into, like that is basically the test. We need to check if the equivalent loads in terms of thermal media, maybe probably gas or liquids, and whether the construction, the design can withstand these environmental parameters.
Exactly.
Right?
So we have to define tests, right? Very often it's just said we take this and that test, but if my environmental conditions change, I have to adjust the test, right? So in reliability engineering, we typically say reliability or life of the product depends on stress and strength. So the stress comes from the field. I need to understand it. It's project specific. Strength comes from the materials, production. So that's a multi-variable game. And that we need to be specific. And if we test something, actually, testing has a purpose, right? So the test must be derived from what we have in the field and the damage mechanisms that are in the design.
All right, so basically, if we design something somebody could think of, well, I will sit on my product and imagine how it feels out there doing its job, and then trying to abstract that into a set of tests. And the question for me is how the designer can overcome these traps and issues. How, like, he would technically would also have to be kind of a test engineer, or at least half test engineer, or be educated to know what mechanisms actually work there. Now we are in an industry where being a designer is not, like, at least in Germany, you wouldn't go to university and be a designer, PCB designer, for example. You learn that, like, just doing it. How could we support that? Is that the same way in the US? Is there any courses or coursework on that?
I believe we're more on the chemistry side. I believe there are classes, certifications that can be made, but it's not. You don't get a PhD in circuit design, right? A lot of it is certifications and then on-the-job training, as you mentioned. And it's wisdom, it's experience, but it's curiosity in challenging some assumptions. And your background a little bit with through-hole, those components are normally very high off the board. They have a totally different manufacturing challenge than a leadless QFN or a 3,000 ball BGA. And so it's understanding and being curious to say, oh, how is this component different? What do I need to do? How manufacturable is this? The 01005s, now those are so small. When you look at trying to clean underneath those, you might only be at about 0.5 mil or 12 microns. We were talking earlier, the silk screen around there becomes a speed bump. It's risking. And so again, it was great to have silk screen around surface mount components when people were manually placing these, or for certain identifications. But it's challenging some of those assumptions, saying this is the way that it's always been done. Now with a lot of AOI and other inspections, you might want silk screen in certain areas, but around flush mounted components, is it necessary, and is that something that can be removed to make that more manufacturable?
Shall I? Yeah, I would like to add to what Ram said, actually. It's like what you said. You mentioned the terms curiosity, experience, right? And who collects that experience, or who is curious? Typically it's specific single persons, right? And the company benefits from that knowledge as long as the people are working in the company. But that's not a sustainable concept, because when they are gone, when people leave company, there is fluctuation, all the knowledge is gone. And that's the idea of having kind of a reliability process where we say we have to make it sustainable, right? There must be a base foundation. Of course, people, when we train people, they do not know everything. Many things are then experience driven, but there is a sound foundation of knowledge. And the idea to run a process parallel to the design phase, to the production planning phase, incorporating all these things. And I would say that's mandatory for having a chance to come up with a reasonably reliable product.
Great, great. When you look like 5 years from here, how do you feel reliability and cleaning will eventually merge more together? Or what do you think, where will we stand within the next 5 years? What's going to be changing? I mean, obviously you have been doing a great journey throughout your professional lives already. You know what has been, where we have been 10 years before. What do you feel, what's the next trends on that? What's your thoughts?
I'll start here. I think a lot of things, especially in the cleaning world, tends to be a little bit reactive towards the material sets, the materials that are being used, the different green materials that are sustainable materials that you're building the components out of. I think, to your point, you need a process. And so what my concern is that a lot of young engineers are just going to go to ChatGPT or Copilot or something and say, what is my answer? And that's,
Have you tried it out? Have you tried it out?
Yeah, there can be some great information, but it can also be some very wrong information. And again, it's amazing how much better that technology is becoming.
Sure.
But I think we need to be careful to be too reliant on that, and continue to create, educate the actual engineers and the people and develop a process, and almost have a reliability index or a cleanability index, and that would be nice for components in looking at, okay, well, if I'm going to put this component on this board, here are the things that I need to consider.
I would say that's absolutely correct, because we have to be honest. We have to be honest in terms of what we know and what we don't know. And if we don't know, I would say it's a bad idea to go to ChatGPT and hope for the right solution, of course. Unfortunately, we live in strange times where that more and more becomes a reasonable solution for many people. But typically in engineering, it was always the same since ever. What we know, we know. Basing on what we know, we can compute or simulate. And what we don't know, we have to test, right? And of course, if we get new materials, then we have new challenges. And if we don't know, we test. That's it. So I would say good old engineering is very often the answer, and also in that new times.
I like that categorization, because there's always a blind spot. And I now understood, or you put it in great words, I think, all those things we know we can simulate. We can build models. We can build an index for cleanability. We can calculate solderability today for a through-hole, for other things. That's feasible. But there are still things. There's variance in the world. There's variance in materials. There's variance everywhere. And there will arise some blind spots, some things we don't know. And therefore we do need testing. And even great software, simulation software like Sherlock and so on, they cannot cover everything. So great. Thank you very much for your discussion. Thank you for joining. And one thing I think we can conclude with is stay curious about the mechanisms and designs to improve your reliability in your products. Thank you.
Kaizen is the leading global supplier of award-winning cleaning chemistries for electronics assembly operations. Whether you are cleaning stencils or final assemblies, our global team of cleaning experts is there to help you succeed. Want to know more? Stop by our booth or visit